Great. It's my pleasure to introduce Yoshiki Nakamura from Tokyo Institute of Technology, and he will talk to us about expressive power and succinctness of the positive calculus of relations. The floor is yours.
Thank you for your introduction. So, hello, I'm Yoshiki Nakamura from Tokyo Institute of Technology. Today, I am going to talk about our paper, Expressing Power, Expressive Power, and Succinctness of the Positive Calculus Relation. So, this paper's starting point is the following equivalence shown by Tarski and Jivand. That is that Tarski's calculus of relations and three-variable first-order logic have the same expressive power in terms of binary relations. So, for example, we can translate COR terms into FO3 terms as follows. Here we use this bracket notation for making a first-order term from a first-order formula. Here the sub x is used for the first argument, and the sub y is used for the second argument. For example, the converse in the calculus relation can be expressed by this term in first-order logic. Converse is the operation which swaps the pairs of a given binary relation. So converse can be expressed by a first-order logic formula by swapping variables from x, y to y, x. And Boolean operators in the calculus relation can be naturally encoded by logical operators in first-order logic. Complement can be encoded by negation, and union can be encoded by disjunction like this. And also, the relational composition operator can be also naturally encoded by using the existential quantifier and conjunction like this. So in fact, three variables is sufficient. For example, we can translate this term into first order logic with three variables x, y, z, like this. By using variables inside carefully, we can translate into three variable first order logic formulas like as follows. So in fact, we can translate COR terms into FO3 terms by the standard translation in linear size, which is defined like this. Here we use top for the universal relation and bold 0 for the empty relation and bold 1 for the identity relation. And we use dagger for the dual of the composition, basically like this. And also we use pi, T-pi for a projection operator of the binary relation, which is defined or given by like as follows. This is a generalization of the converse operator inspired by first order variable as follows. So each projection operator is an abbreviation of a term using converse operator or identity relation like this. So our motivation is the following. So how about positive fragments of COR and FO3? So the positivity is also interesting in the view of the desirability like as follows. So, but now today I am interested in the expressive power of the positive fragments. So by using the standard translation, we can translate from positive calculus of relations into three variable positive logics. For example, terms of primitive positive calculus of relation are the terms is constructing from these operators. In other words, allegory terms with top, which is in these papers, can be translated into three variable primitive positive logic formulas. Also, terms of positive calculus of relations can be translated into three variables existential positive formulas. So furthermore, if we extend PCOR with transitive closure operators, it can be translated into three variable existential positive formulas with variable confined monadic transitive closure. However, the converse direction is not trivial. So at least we cannot use the Tarski-Java translation and some known translation directly. So our contribution is to reveal this direction completely. So first, we present translations from positive three variables logics into positive calculus of relations. As for efficiency, for the below one, the translation is linear, but for the above two, the translations are exponential. So second, we show that actually the exponential blow up are not avoidable. So namely, there does not exist any precise translation from this to this. In that sense, our translation presented in this paper is an optimal translation. So first, we present a new translation from FO3 to COR. So before we present a translation, we define syntaxes of the calculus relations and first order logic. The above, intuitively, the above operators correspond to the below operators like T corresponds to TT and like that. And here in this form, in this form, X and Y are distinct, and phi is a formula having at most three variables X and Y. And this denotes that binary of T on a structure M, where M is a binary as a structure of binary relation. So we say that two terms T and S are equivalent when Y structure, the binary relation represented by T and S are equivalent. In the following, we present the outline of our translation from FO3 to COR. So first, we translate FO3 term into negation normal form. Second, we substitute each existed psi with conjunction of formulas such that each row each row has at most two free variables. Third, we push quantifiers into the formulas as much as possible, then we can translate into COR terms by simple structure induction. So here, this part is only exponential. So we give each steps. For the first step, by using De Morgan law and the double negation elimination law repeatedly as much as possible, then push logical not symbol deeper into the formula as much as possible, like by using these rewriting rules. Then logical not applies only to atomic formulas. And next, so for the second step, for example, let's consider this formula. Then note that this part violates above rule because it has three free variables, x, y, z. So we translate this part by using distributive property of or like this and like this. Then each part has at most two free variables. So we translate it like this. So in the same way as for all, we can translate in the same manner for exists, like as follows. So precisely the translation can be given as follows, but we omit the details. So please see the our paper. So now for third step, we push quantifier deeper and deeper. So for example, let's consider this formula. Then note that by the second step, each formula has at most two free variables. So by permutating appropriately, we can order the formula like this. So this part has free variables x and y, and this part has x and z, and this part has z and y. So then because free variables z does not occur in this part, so we can push this set deeper into this like this. So the third step is from this to this. And combining the steps above, we can translate into the following formula set. So intuitively, each subformula has at most only 2 free variables if the formula in this set. So the remarking point is that existential quantifier is only used in this form, and vowel quantifier used in this form. So this form is equivalent to that of the conjunction in the calculus of relations intuitively. And this is equal to the Dagger operator. So we can translate into COR terms by simple structural induction like this from this set. So by these 4 steps, we can obtain a new translation from FO3 to COR. So as a corollary, we have obtained these translations. So for the below one, the translation is linear because the second step does not use in this case. And this case uses the second step. So the exponential size blow up. Okay. So as for the transitive closure extension, we can easily extend the translations we presented. So it is trivially given by replacing the transitive operator in COR with the transitive closure operator as a variable confined monadic transitive closure in logic. And by replacing the monadic transitive closure in logic with transitive closure operator in COR in a natural way. So we have obtained, we can generalize, we can extend for the transitive closure cases in a natural way. And furthermore, as a corollary, we can generalize the expressive power equivalence like the quantifier alternation hierarchy in first order logic. So let us consider sigma n3 and sigma ncor as analogies of sigma n. Then we can show that sigma n and sigma ncor and sigma n3 have the same expressive power by using the same translation like this. So second, we now consider about the succinctness of PCOR. So the goal is to show this theorem. So there is no too small or n size translation from EP3 terms to equivalent PCOR terms. So for example, let's consider this EP3 term. So then this term can be translated, then this term can be translated into a PCOR term by using step 2 and step 4. So here, the pair ij is a partition of the set n. So because the number of the partition of the set n is exponential, so the size is exponentially blow up, unfortunately, from here to this. So based on this observation, we construct hard terms. So let Tn be the following term. So intuitively, this part is based on the previous one, and this part and this part are for covering all the pair of distance 0 and distance 1. So this is due to some technical reasons for the proof. So to show this theorem, we actually show this lemma. So, but I apologize that the Tn written in the paper's version has a bit error. So I am considering to So a minor revision version of this paper. So now to show this lemma, we introduce the following parameter Wn. So Wn is the number of the structure in this form, such that there exists a path of S from node 1 to node 3. So here note that WNTN is 2 to n. So this is thanks to this blue part. So we showed this lemma. So for every PCO term S, if this inequality holds, then this inequality holds. So if this holds, so when S equivalent to Tn, then so the size of S is at least exponential in n. So by using this equality, so the above lemma can be proved by this lemma. So to simplify the proof, to simplify the proof of this lemma, so we only consider projection normal form. So we can easily, projection normal form is from this term to translating this from this term to this term. So we first replace projection with converse, like this translation, by using this translation, and then we push converse operator deeper and deeper by using this rewriting rules. So then we can easily obtain the PCO terms in projection normal form. So we show this lemma by induction on the structure of S. So the base cases are trivial. So we focus on these three cases. So union and intersection and composition. So for running induction, we use these three lemmas. So these are easily shown by considering the contraposition. So the first lemma is trivial. So by it holds, this holds in general Tn. And for the second lemma, it is shown by taking the parallel composition of counter model for S1 from this and S2 from this. And we can obtain counter model for S1 cup, S1 intersection S2 like this. So we can show this lemma by using the counter example counter model. And for the third lemma, it is shown by taking the series composition of a counter model for S1 and a model for S2. So we can obtain a counter model for S1, S2 like this. So so this assumption used for constructing a this model. So if this holds, then this holds. So we use this. And so otherwise, so this case is also shown by like in the same way like as this case. So these two does not hold in general T. So but thanks to the definition of Tn, so these two hold. So we define Tn for satisfying them. Now we prove this lemma using these three lemmas. So first, the case of union. So then this inequality holds. It is because so if there exists a path of S1 union S2 like this, then there exists a path of S1 or S2. So this inequality holds, and then we can apply induction hypothesis to these two by using the previous lemma. So this part is proved. For the case of intersection, so this inequality holds. So it is because if there is a path of S1 intersection S2, then so S1 and S2, there is path S1 and S2 from this to this. So then we can apply induction hypothesis by selecting L as satisfying this inequality. So such a L always exists by the previous lemma, so this part is proved. So finally, we consider the case of concatenation. The case of concatenation is a bit non-trivial. First, note that if there is a path of S1, S2, then there exist three cases like this. And similarly, so if there is a path of S1, S2 for distinct two versions, then there is 9 cases like this in the same way. So, but actually, so this case and this case only occur. So it is because, so for example, let's consider this case. Then the structure obtained by merging these two structures like this is a counter model of this inequality. So it is because the distance of these two nodes is greater than 2. So this case does not occur. So also let's consider this case. So then in the same way, the structure, let's consider the structure obtained by merging these two structures like this. Then this is a counter model of this inequality. So this model has two new paths of S1, S2 like this. But actually, so one of them contradicts this inequality. So when I prime is greater than I, then this path contradicts this inequality because so I union J prime is directly subset of the N. And in the same way, so if when I prime, when I is strictly greater than I prime, then this path contradicts to this inequality. So we use, we can show so one of them by using so one of them, so we can show the contradiction of this inequality. So therefore, this case and this case only occur. So when so Wn S1, S2 is at least 2, this inequality holds. So by using this observation, so we can show this part. We can show this part. So this lemma has been proved. So hence we have proved this lemma. So from this we have proved that there does not exist a polynomial size translation from EPC to PCOR. So as a corollary, we can also show that succinctness was transitive project case. So this can be shown that this lemma, we can easily strengthen this lemma from PCOR to PCOR TC. So it is because when this case, so S1 we can show that WNS1 star is equal to 0. So this is easy. So the contraction. If not, so this we can show easily show the contraction. So and so we have shown the succinctness gap between positive case, but it remains open for general cases. So it is because our proof in this paper is based on model construction relying on the positivity. So this case is open. So conclusion, we have shown the expressive power equivalence and succinctness gap. So future work are to show succinctness gap beyond positive cases, and conversely to show some complexity gap between PCOR and EP3, and also to construct some PCOR corresponding to EPK. So that's all. Thank you.
Thank you very much. Feel free to unmute and reaction. So nice talk.